We had the Einstein equation.
You seem very excited about that. Yeah. I don't think we're going to reach it in this session, unfortunately.
So this is the Einstein equation. And this is so-called Ricci tensor.
Yeah, here we're supposed to solve for like the metric tensor, right? That's
this one is a function of the metric. And the Ricci tensor comes from the Remon tensor when, say, the first index is contracted with the third index.
So it's a special case of the Remon tensor?
You sum over it. The Remon tensor has 4 indices, and you contract 2 indices, which means you make them equal and you sum over. Oh. And this is actually a simpler tensor, and that is in fact all what you need in general relativity.
Right, so it is like a special case of the Remon tensor where the first and third index are equal, so we can sum over them.
It is a function of the metric tensor. If it is some derivatives of the metric tensor, you can express it in terms of the Christoffel symbols. It's a complicated, it's not terribly complicated, but an expression you forget, right, which you have to look up every time when you use it. Because, let me write it down. I have it in my notes somewhere here. It's good to see it because then you know, I think, yeah. Yeah. Oh, where is it? Oh, here's the Remon tensor. These are very long equations. So here I have this is actually the Remon tensor, but I want to have the Ricci tensor.
Oh, there's some latex over here?
Yeah, that's because I didn't have, here I have one. Okay, so it's always hard to find. So we can have this one, the Ricci tensor, or the Remon tensor. So that is, I wrote it as R, A, B, C, D. Is that right? Yeah. So that is dB gamma DAC minus DA gamma DBC plus gamma ECA gamma DEB minus gamma ECB gamma DEA. So this is the Remon tensor, and then you make say this index equal to
I think you're setting A equals C
here. I defined it as the second index equal to the third index. Oh. So the Ricci tensor R mu rho, I defined as with a minus sign as R mu nu rho. It's a little bit different. I did it here, but it doesn't matter because it is anti-symmetric under these two. When you interchange these two, you get a minus sign, and that's why I have a minus sign. And then you see it. You make 2 indices equal, sum over, you get a similar expression. That is what it is, and it is complicated. And this Christoffel symbol, that is gamma, say A, B, C, is, and I also need a cheat sheet for that. Otherwise, I get it wrong. because that is also a complicated expression. I have it here, and I use different indices. So this is the gamma. Gamma sigma mu nu is minus 1/2. This is the metric tensor. Sigma rho times d rho g mu nu minus d mu g nu rho minus d nu g rho mu. So it's also a complicated thing. So it has 3 terms. So that means this 3 terms, 9 terms, 9 terms. That is 18 plus 6 is 24 terms.
That doesn't sound like something I would want to evaluate by hand.
No, there are good computer programs for that.
Right, like Mathematica.
Yeah, Mathematica. You should learn how to use Mathematica because that is fun and you can do many things with it. So what we discussed is what the Remon tensor is actually doing. It has to do with covariant derivatives. That is, if you have a covariant derivative, they do not commute. This is not equal to when you do it in the other order. And the Remon tensor tells you how it does not commute. If you have, if you look at these two minus this one, and you act with this on a vector, say omega c, then this is equal to r a b c d times omega d. So that's the definition of the Remon tensor. So last time we looked at an infinitesimal loop and looked how a vector is actually changing, and by expanding that you actually find you find this expression, and so we derived kind of the Remon tensor last time. So actually what I wanted to discuss, because last time I want to discuss some of what you actually can do with this equation. So how you can see there are black holes in this equation.
Oh.
And so it's a very complicated equation. You see all these many terms. This has 24 terms, that has 24 terms. This term, there's also the gravitational constant. This term is the matter.
Right.
That is what weighs has mass. So to solve it, in the first place, you have to solve it in vacuum, when there's no matter. That's what you do. When you do physics, you always first look at the simple cases. And when there's no matter, you think there's nothing, it is not important.
So is this like the identity, the T mu nu?
No, when there's no matter, it is 0.
Oh, okay.
So no matter. For example, if this is a black hole, then here there's no matter. So basically, everywhere around a black hole, there's no matter. So you only have to solve an equation with no matter, with the right-hand side equal to 0.
Right, but isn't the black hole itself like considered matter because it's kind of a point mass?
Yeah, but we solve it only outside. That's the trick.
Okay.
But then we make some assumptions, because what we have to solve is the metric. G alpha C beta is a metric, and it depends on space-time. It's a function of 4 coordinates, and we have to solve for that. And you think you know some properties of that. And what do you think, what you know about the functional dependence of the metric tensor?
Functional dependence?
Yeah. So it depends on these coordinates.
The space-time interval. Oh, right. We derived that formula for the metric tensor a while ago.
Yeah, but this is, if I draw it a little bit neater, so it is everywhere the same, right, because so a black hole has no structure, and that means it should be in all directions the same.
So we can consider like for x mu, x equals y equals z, or x1 equals x2 equals x3.
Yeah, it only depends on the r variable. So g alpha beta right. is a function of r. And what you also think is that a black hole doesn't change.
So it's not a function of time.
Exactly. So it is only a function of this. And that simplifies things a great deal. Right. So what you know is that if you have the metric, it is equal to say a minus, say f1 of r times dt squared plus f2 of r times dr squared plus r squared times, you know what this notation means? D omega squared. D omega squared is equal to sine squared sine squared theta d phi squared plus d theta squared.
Oh, so we're kind of doing this as if we were in polar coordinates?
Yeah, in spherical coordinates, and we assume that because there's spherical symmetry, it can only be that. Mm-hmm. And by assuming this form of the metric, life becomes much simpler. So in fact, we only have to solve for two functions instead of these are, it's symmetric, there are 10 functions. Right. It's 10 functions that depend on 4 variables. We now have only 2 functions that depend on 1 variable.
Yeah, and that's something you can work out by hand. And it isn't dependent on theta either, so we can take it to be a constant, right?
Indeed, we will get to that, because we know in gravitation, if you ever have this the sun and there's a planet, the planets are always moving in a plane, and that means that
phi is constant and theta is changing.
No, this is the phi angle. So indeed, theta, if this is the axis, theta, then theta is constant. So theta is equal to pi over 2. It's 90 degrees.
Oh, the same trick we used before for the geodesic, right?
Yeah. So and that should also come out of the equations. And that is actually a famous law in nature, angular momentum conservation.
Oh, yeah. Conservation of momentum, conservation of angular momentum.
Yeah.
I'm sure my dad knows something about that.
And that is the reason. That is the reason that you don't fall from a bicycle. That's the angular momentum. Yeah. Because if there was around a black hole, the angular momentum is conserved.
Yeah, the conservation of physical quantities is very interesting. My dad loves classical mechanics, so.
Okay.
He knows a lot about it.
Yeah. So it is still not simple. And I'm getting just my notes on this. It is still not simple. Although, and in fact, you can have some other combinations, because what you also could get is there should be rotational invariance. And for example, if you have x dot dx squared, that's rotational invariant.
Yes.
Because and so the full dependence is in fact, I call this f of r times dt squared minus 2 e of r times dt times x dot dx plus dr times x dot dx squared plus cr times dx squared.
Are all these function names actually symbolic, or are they?
No, they can be just a name. Can be any. You can name it anything.
Right.
But
they're distinct.
These are the most general rotational invariant terms you can write down. But you can simplify it, because what you can do is you can change the time coordinate, and I did that as t prime is t plus phi of r. And that is what you always do in general relativity. You use coordinate transformations. So that is dt prime is then dt plus phi prime of r dr. And that means if you square dt squared,
dt prime.
Hmm?
Dt prime squared or dt squared?
Yeah, I want to express everything in the primed coordinates. So you get that. And this is r squared. So it's 1/2 dr squared is equal to r dr. So it's just actually r dr, and that is what we have here. We have here, so this is r dr. So what you can do is that you can tune this phi so that this whole term cancels, and that is what we are going to do. So we already don't have that term. For this one, that was equal to r dr. So this is equal to r squared dr squared, and here we have dx squared. That is like dx squared dy squared dz squared is equal to dr squared plus r squared times d theta squared plus r squared sine squared theta d phi squared.
Wait, I'm not. I know. I don't think I was listening, but I'm not entirely clear on how we get from this step to this step.
This is just a scalar, just a dr. You differentiate, just change dr. There's a square comes down and becomes dr.
Oops.
So you work with differentials instead of derivatives. And now, what can we do? So what we would like to have is that it would be just r squared times d omega squared. To actually change the coordinates once more so that the prefactor for the angular part just becomes 1. So we change our r coordinates, and I call this what I did is r squared times cr is equal to r prime squared. That's also a new coordinate. Then what we have then is just this term. We have this term, that's a dt squared term. We got rid of this term, and this is an dr squared term with some function of r. Here you also get a function of r, and you can combine them into one function of r. So in the end, you get this form, and that is what I got here. In the end, when you do that, you arrive at this form. So this form is the most general form you can get. And then you can, because now we know what a metric tensor is. So the metric tensor, it is diagonal because there's d phi squared, d theta squared. So in this case, the metric tensor is g mu nu is equal to minus f1 in this case, then 0, 0, 0, 0, r is the second coordinate, that is f2, 0, 0, then theta is the third coordinate, so it is 1, and then phi is the last coordinate, that is sine squared of theta. So this is the metric tensor.
Right. So
it is greatly simplified. But what we have to calculate is this thing. That means we have to calculate this thing, and we have to calculate that thing. And there are still many things. They are not simple. In class, I did only one example to calculate that, and the rest I copied from a book because it is just too complicated. There are too many terms, and I should look at the time we have. And
7:10.
yeah, so there are too many terms. So I want to go to the solution, to discuss the solution you have, because we know it should be of this form, because we look at a case where there's no matter, there should be rotational symmetry. And let me, I can erase this. So I just want to write down the solution for a black hole metric. And that is ds squared is minus 1. And I should make sure I don't make mistakes, because you can always make mistakes. Radius divided by r dt squared plus 1 divided by 1 minus rs over r times dr squared plus r squared d omega squared. That is what you get if you solve the equation. That's solution of the equation. It is very simple, and rs is equal to 2 times the gravitation constant times the mass of the object.
Right.
And now you see the problem. When r becomes rs, this blows up, and so r equal to rs, things blow up.
Oh, so everything's broken. Because we have 1 over 0.
Here there is 0, so that means that kind of the time doesn't do anything anymore. So if you change the time, ds doesn't change. And this is the Schwarzschild radius. If you are for r less than rs, you are stuck. So rs is also called the event horizon.
So that term suddenly becomes negative if r is less than rs.
Yeah, but that's still okay.
Yeah, but the worst thing is when r is equal to rs.
Yeah, it is still okay because we don't know yet if this singularity is due to our choice of coordinates. And in fact, it is not a real problem because we have to change our coordinates. But we cannot discuss that. That's again a complicated story to go to the right coordinates, to go through the event horizon. And that is what you can do. But you actually can understand this. And the way to understand that is if you look at the escape velocity. The escape velocity is when the kinetic energy is plus the potential energy, which is negative. That is g times n times m. So there's a mass here, and we calculate the escape velocity of a smaller mass, and this is the gravitational potential. Say that is r at distance. And the speed, we know that v is less than c. So we are going to calculate the distance r to a gravitational body when you can no longer escape with the speed of light. And that is when this is equal to 0.
Oh, I've seen that before.
So what you get is r, this becomes c squared, is equal to 2 gm divided by c squared.